So we're talking today about rates of reaction, and we're going to look first at the ideas that you were introduced to at GCSE and then move on to how we think about it at A level. So before we do anything, we need to think about what has to happen before molecules can actually react together. And at GCSE you did learn about something called collision theory. Molecules have to collide before they can react. But it's not just about colliding. Molecules need to collide with the correct orientation, and they need to have enough energy before they can react. We call this the activation energy. And at GCSE you would have learnt about the factors that affect the rate of reaction. There's a few ways that we can change it. One of them would have been to increase the concentration. If you're looking at a reaction that involves reactants that are dissolved in a liquid, then if we increase the concentration of one of these reactants, then the rate of reaction could increase. That means because you've got more crowding of the reactants, there's more of them in a particular volume, and so they're more likely to collide with the other reactants, and therefore a reaction is more likely to occur. Now they still need to have the correct amount of energy, they still need to have enough energy, they still need to collide in the same way, but if there's more of them crowded in a particular room, then it's more likely to occur. And the same reasoning follows for gaseous reactants. If we've got gases reacting together, if we squeeze them into a smaller volume, then they're more likely to collide with each other. If we increase the pressure by decreasing the volume, then the reaction rate will increase because collisions are more likely to occur. And so we can also increase the likelihood that collisions will occur by making the particles move around more quickly. If we've got particles moving around more quickly, they're more likely to bump into each other. And the way to, one of the ways to increase the kinetic energy of a particle is to increase the temperature. So by increasing the temperature, we make particles move more quickly, and the rate of reaction increases. The other reason that increasing the temperature increases the rate of reaction is because more particles will have the activation energy. There will be more particles that have sufficient energy for a reaction to occur, and we're going to talk about that in more detail later when we look at something called the Boltzmann distribution. Another way that you learnt about at GCSE of increasing the reaction rate is to increase the surface area where the reactions will occur by decreasing the size of solid reaction particles. So if you have something like marble chips, is something that we talk about all the time. If you have large lumps of marble, they will react much less quickly than if you powdered the marble, for example. If you powder something, it has a much higher surface area. And the way I talked about this in class is I got a crunchy bar and some Maltesers, and if you break up a crunchy bar, then you're going to have two extra surfaces to put some chocolate on. There's more surface there. Break it again, there's another surface there that wasn't there before. So by making the crunchy bar smaller, you increase the surface area until you get something like the size of a Malteser. There's loads and loads of chocolate there because we have a greater surface area. So a smaller particle size means a bigger surface area, and that means that there's more chance for the particles to collide with each other. There's more places they can do that, and then the reaction rate increases. So at GCSE you would have talked about how to measure the rate of reaction, and basically we need to look at how quickly either a reactant is used up or a product is formed. And if a gas is made, then we can collect it either in a syringe or in an upturned measuring cylinder by the displacement of water. We just measure how much gas is given off in a particular time. We can plot the amount of gas being produced over time using something like a gas syringe. And again, we'll get a curve. Now these curves start off with an initial steep gradient. The initial rate of reaction is always the fastest. We've got the most reactants around, we've got the most reactant particles that can collide and react. And then as the reaction proceeds, the rate of reaction decreases. We can see that the gradient decreases until it flattens out. And when it's flattened out, then we know the reaction is finished. There are no more reactants that are colliding, no more reactants that are producing a gas or whatever product it is that we're measuring. So this is the classic shape of a rate of reaction curve. And these reaction curves can also give us an idea about the reaction conditions. So if we have a high concentration or a high pressure, then the initial rate of reaction is going to be much higher than for something with a lower concentration or pressure. There's going to be fewer particles around to bump into each other and collide and react with a low concentration or low pressure. So the initial rate of reaction is going to be lower. The gradient will be less steep, and so we get different shapes of the curves. And the final point to notice is just that if it's only the concentration or only the temperature that's changing and everything else is the same, so the amount of reactants is the same and so on, then the volume of gas that is given off at the end is the same. It's just how quickly you get there.